lumped capacitance. Let's finish the last example. So, okay. So in lumped capacitance, where we didn't finish last time was this example in which we have a computer chip, and there were two questions. Number one, what is the running temperature of this chip? And we said that although the air around it is at 20 degrees C, the chip heats up to some other temperature. And we wrote the equation for those temperatures. That goes on Wednesday's exam. That does go. And if you look at the video, we made it up to there. Now, then I have another question that I'm going to address only partially here, but we'll see the same question again, is if the chip is running in steady state and the fan breaks down, what is going to happen? And we know what's going to happen. The chip is going to overheat. And then it asks, what is the time for failure if failure happened at 100 degrees? And in this, that is, I wrote it with quite a bit of attention to detail. So please take a look at this example that is written in detail. But at the end, I have this graph. And this graph can look intimidating. This is a real engineering graph. But the point of this part of the class is that to see things that might look at first sight intimidating and have the sense that we can tackle one step at a time and understand it all. This is the most important thing in this class. And what we're going to see in this class, in this week, starting today, is something that definitely can look intimidating as we look at differential control volumes. But if we go one step at a time, we're going to make sense out of them. These things we're doing now are not things you just read with floating attention. This is not like English literature. You need to go step by step, and the way we engineers make a difference from other people who are intuitive or good with their hands is that when the problem gets beyond intuition, we can go in a stepwise manner and conquer the problem in a systematic way. So let's look at this at this graph here. In this graph here, the horizontal axis is time. The vertical axis is temperature. And this problem, you see kind of two curves. First one here, lower temperatures, and then another one, higher temperatures. Let's split them and look at them separately. The first curve starts at 30 degrees. That is at the time in which we would turn on the computer. And we said it started at 30 degrees. And although the air is at 20, we saw that no, it doesn't go from 30 degrees to 20. And the reason it doesn't is because the chip is generating heat. And this heat needs to be evacuated, and that increases the temperature of the chip such that it has losses to the environment. And so it starts at 30 and will go to a higher temperature. That is the temperature of steady state. And we don't even need to solve the differential equation for that, because in this equation that we did get to write, when we say, okay, steady state is the derivative of temperature with time is 0. So this goes away, and this equation is not a differential equation anymore. It's an algebraic equation, and we can solve temperature from here. And sure enough, we solve it, we get this value, this formula here. And that formula would give us for a convection coefficient of 100, assuming that the forced convection from the fan has a coefficient of 100 watts per meter square Kelvin, this says that the chip would be operating in steady state at 73 degrees. Now, if, for example, the fan were to break, now the convection coefficient, instead of being 100 watts per meter square Kelvin, would be 10 watts per meter square Kelvin, much less. And we have the convection coefficient down here. So if it's smaller by a factor of 10, this factor here would be higher by a factor of 10. And here I found a typo. This small t is mistaken. It should be a big T for temperature. And then the calculation indicates that the chip in steady state with a broken fan would be running at 534 degrees C. Of course it doesn't, it melts before, right? But these are the expressions that you should not memorize, you should not even attempt to memorize, but you should know they come from writing the energy balance. And this energy balance in steady state, we take this term out and we solve this simple algebraic equation. When you get to see these final expressions, they can look intimidating, but it's a little bit like extreme sports. You might be scared, but the first thing you need to know is just control yourself, right? So this is something that if I showed it to you without saying where it comes from, it's like, what is that? But we know where it comes from. And we know that we got here one step at a time, and each step was something that was very simple. So we got here by combining what we learned on week 1 and what we learned on week 2. Energy balances in week 1, heat transfer mechanisms in week 2. That's it. And we put it together in week 3 to get these things like this one here. Now, in this graph, this steady state temperature is this temperature at which it stops evolving. And we know that we're going to have this exponential evolution. And the exponential would come from solving the differential equation, which is first order, linear. We know how to do a change of variables to get it homogeneous, and we would get it. But more important than solving the differential equation is to know that where it starts, where it goes, and how fast or how slow it goes to its final stage of a steady state is with the constant of time, with a time constant, which we had seen too from when we wrote the equation, right? When we rewrite it this way here, that is the time constant is going to be this 1 over k that we have here is 1 over this. And we saw this on Wednesday last week. So now we know how to calculate this slope. We know where we start, we know where we finish. So we know pretty much everything about this part here of the curve. We understand it. Now the computer is running for a time, whatever time it is, and we said the fan breaks. If the fan breaks, now the heat of the chip is not evacuated as easy because the convection coefficient is much lower. The heat out is much smaller. So the chip is going to go to much higher temperatures. How much higher? Same calculation again, right? With what we did before, and it gave us 554 degrees, which is ridiculously high. And it's going to go, once the fan breaks, there is going to be a time constant associated with it, which we know how to calculate because we saw it on Wednesday last week. And we start, in this case, now we don't start from 30 degrees or 20 degrees. We start from the steady state temperature at which the chip was running. So this bigger curve here is the same as this bigger curve, this smaller curve down here. Both have a start, we know. Both have an end, we know, a steady state, we know. Both have a time constant associated with them. It's the same problem twice. Now, in the case of the second curve, what I asked is something similar to what was asked in the problem of snow making, is if we have this exponential decay or this exponential increase, at what point do we reach a particular temperature, right? For that, we need to solve the differential equation, but we know it's this exponential here. And if we do this exponential, and we have here, we can solve now for time, right? And this log here is because we're solving for this exponential, and we can calculate the time in which it reaches failure. Because we were starting at 73 degrees and it fails, we said, at 100 degrees, right? Modern chips would fail at lower temperatures. So we have to calculate how long does it take to increase this little amount of time. And that is very small. It's of the order of 21 seconds. So if you have a gaming computer, we stop hearing the fan, count 21 seconds. You have 21 seconds to turn off the computer before bad things happen. And this is with a Pentium chip that is very old and therefore more resilient. Modern computers might be even faster. I don't have the numbers for those, but 21 seconds cannot be all too different than that. So I wanted to go over this graph with you because graphs with this, like this, if you look, are in pretty much every exam in previous years in which I asked the students to make the graph. Now I will not ask you to make a graph, but you will need to identify critical parts of the graph. In particular, the temperature at which it starts, the temperature of steady state, and a time constant associated with getting there. And what if I ask you for a particular temperature or a particular time, how does it correspond? If I give you a temperature, how does it correspond with the time? Or if I give you a time, how does it correspond with the temperature? And that's lumped capacitance. And we can do amazing things with those. All right. So we will have office hours today at 2, tomorrow at 2, and Wednesday at 9 a.m. And if anything is still if there is anything that we still wish to discuss further, we'll have plenty of time to do it. I will switch now to the topic of this week. That is the same energy balances we have done before in week 1, and then we recycled in week 3 for lumped capacitance. We're gonna see what happens when we cannot say that the body is at uniform temperature and we need to make much smaller energy balances to account for it. All right.